Welcome to ECEN 215's Principles of Electrical Engineering. Today we are going to be talking about current, voltage, and power. This is a review of most of what you would have learned in your physics classes, so it would be understandable that some of this you would have already seen and already understand. So there's going to be really no new concepts being discussed in this lecture here. So let's go ahead and get started. So first we're going to talk about electrical current. So when we talk about current, it is the time rate of flow of an electrical charge through a conductor or circuit element. As we were covering the other day in the first lecture, and we were talking about the analog of fluid flow, where fluid flowing in a pipe is the equivalent of charge flowing through a conductor. The same concept. As such, we have a reference direction. We have a conductor or the circuit element that we're interested in, and there's a cross-sectional area of that conductor. And so we're interested in the charge that flows through that cross-section, if you will. So in this case, we're looking at the units for current, which is amperes. It's named after a gentleman named Ampere who discovered all of this. And it's equivalent to coulombs per second. That is the rate of charge per unit time. And a charge of an electron is, from physics, you might remember, is minus 1.602 times 10 to the minus 19 coulombs. So let's take a look at that real quick. So let's redefine this in a mathematical form now. So what we have is what we just talked about, but now using calculus. I of t, which stands for the current intensity, and this is an important concept that we will represent current in this class with the letter I. And that stands for intensity, which is actually a French term, a current intensity, and so that's where the letter I comes from. And it is the derivative of the charge and the change rate of charge over time, so dq dt, derivative of the charge given time over time. And of course, if we knew the current and we knew the initial state of charge, we can back out the actual plot of the charge as a function of time by taking the integral of that from time t naught to t. So let's just do a quick example. Suppose that we were given a charge of time versus a certain circuit element as given by this graph here. Q of t in coulombs is this. It starts at, we start at 0 coulombs, and then we slowly look at an exponential curve up to we get to asymptotically approaching 2 coulombs as time goes on, starting from 0 milliseconds all the way up to 40 milliseconds. It's about, and we'll eventually get to 2 coulombs. So we can represent that mathematically as Q of t is equal to 0. For time less than 0. So everything out here is less than 0. Let me turn my pointer on. Everything out here is less than 0. And when Q and T, when T is positive, we start at 2 minus 2e minus 100t. So that's this part here is causing this exponential increase to where it eventually, as t goes to infinity, this term here is going to go to 0 and cancel all of this out, and you end up with just 2. So when t is equal to 0, this ends up being 1, so it's 2 minus 2. So it will exponentially increase. If you wanted to, you could actually go and plot this in MATLAB or Python or whatever your favorite mathematical, use your calculator to actually plot this equation. So now that we know that, let's determine what current is. So let's just take these two formulas and apply the mathematics we just looked at. Simply, we take the derivative of the charge over time, and obviously before time 0, it's 0, so the derivative of 0 is 0, so the current is 0 amps for t less than 0. And if we take the derivative of Q of t here, well, this is a constant term, so that automatically becomes 0, so it's 0 minus, and then it's this right here, 2 to e to the minus 100t. So we do derivative by parts. We take this and we end up with 200 e to the minus 100t amps, which looks like this. So initially we have a spike of current, and it slowly exponentially decreases till eventually the current drops to pretty much zero after 40 milliseconds. So there will be some problems in the homework, which will be given various formulas for Q of t or I of t, and you have to work back and forth with the calculus to determine, current intensity, I of t, given Q of t, or if you're given I of t, what is the Q of t given a state of initial charge of whatever. So this is probably going to be, honestly, the most advanced calculus that's going to be in the class is something that's basically these problems. Said there's going to be some couple differential equations that we'll talk over in a few weeks. But for the most part, this is mathematically the most calculus intense we're really going to get is derivatives and integration of basic exponentials and things like that. So it's not going to get too advanced in calculus in here, so don't worry. So let's take a look at this. So we analyze circuits. How do we analyze circuits? Well, we have different circuit elements. We're just going to give them names here, A, B, C, D, and E here. And then we can start by just assigning current labels. So we're going to start by doing current analysis. So we have current 1, and we arbitrarily we've defined what arrow, the basically convention we want for I1. So the current is going to come here, going through circuit element A. Going from this side to this side is this direction of current. So if the current was, let's just say 5 amps, I1 was equal to 5 amps, it means 5 amps are traveling from this side to this side through A. If it was minus 5 amps, then the current actually would be going this direction. And we would just be representing it as minus 5 because we have set the direction of the arrow this way. And this is, as simple as that might sound at first, it's very important that you understand that concept. The direction of the arrow really determines, and you set the direction of the arrow when you do your circuit analysis. When you work out the equations for this, which we'll be going over later in this class, it's very important that you keep your directions the same. Based upon the arrow, because you could do the circuit analysis, like I said, and you determine that the current flowing through element A is actually minus 5 amps for I1, and so the current's flowing this direction. So sometimes you're going to want to just say the answer is 5 amps. Well, no, it's minus 5 amps based upon the direction that was set. So it's very important you pay attention to the arrow and direction. If you notice in this case, I2 is going from this side to this side on element C, and the same thing for current number 3. So let's just start with that. And in the same vein, we can also represent current, so we can represent with arrows, but we can also label it with these nodes. We just have these 2 N nodes for, in this case, a resistor, this element that resists current. And we say the current going from A to B is the current that's going this direction. So we could call this I1 and go this direction, or we could call it IAB, which is current going from A to B, and say that was 5 amps. But current going IBA would be minus 5 amps. So if this was 5 amps as AB, then IBA would be minus 5 amps. So it really just depends upon the direction that you're going. This one here is very important that you pay attention to this slide, because this, again, trips up various students here and there, and there'll be a problem on the test dealing with this. So energy that is supplied by a circuit element, like a generator, a power supply, for instance, that is where the current is going from the negative terminal to the positive terminal of the element. So the current is going this direction, and the voltage, we'll be covering voltage again in just a few minutes, but the voltage across the element is from positive to negative. So if the current is flowing from the negative terminal to the positive terminal, out basically the positive charge, if you will, is coming out this way, then this is energy being supplied by the element. However, if it's the other way around, where the current is flowing into the positive terminal and out the negative terminal, it's going this direction instead, then that is an energy absorbing device, like a resistor. So this side here, energy is coming from negative to positive, that is being generated or supplied, and where it is being absorbed is where the The current is going into the positive and coming out the negative. So it's important that you pay attention to this slide here and really understand the two differences, because you will have questions like, for an energy being supplied by the element, which direction is the current flowing? Is it going out the positive terminal or going in the positive terminal? So if it's going out the positive terminal, it's being an energy supplier or generator, and if it's going into the positive terminal of the device, it is being absorbed. So there's what kind of different types of current we have? We have DC current and AC current. DC current was direct current. There is no time rate of change on the value. In this case, we have 2 amps, and it's 2 amps DC, meaning that it is 2 amps at 0 seconds, it was 2 amps at minus 5 seconds, and it's 2 amps 30 seconds from now. Now this could, in reality, and we all know there's going to be little bumps, and your battery is, we consider it DC, like in your truck or car, but fundamentally it's DC, and it has very low frequency, for technically 0 frequency component. AC circuit analysis is where we look at a signal that actually alternates in time, hence the phrase alternating current, AC. So DC stands for direct current, AC stands for alternating current. So as you can see here, we have a signal that is constantly changing. It actually has a cosine component. And so it is alternating back and forth. If you sum this together, the sum is 0. Because if you take the average of the signal over time, it will be 0 volts or 0 amps, depending on if it was an AC current or an AC voltage. So for instance, the power coming out of the wall, AC power that everyone's used to seeing, is either 240 volts at VAC or 120 volts VAC. That is, if you put an oscilloscope and actually look at the signal coming out of the wall, if you look, put the probe in the hot side, and you put the alligator clip, the ground lead of the oscilloscope, on the earth or neutral lead, you would actually see something that looks like this. You would see a 60 hertz sinusoid with a peak around 165 volts VAC if you went and hooked it up to your home outlet. So here's just a few other examples of current and voltage waveforms. We have a triangle waveform here. This is a triangle current, where the current is actually proportionally increasing over time and then decreases and goes negative and then comes back up. And that is considered a triangle waveform, hence the shape is the name. And of course, a square waveform it's kind of like DC in that it has a very fixed value, and then it automatically changes and goes negative. So this could be 2 amps and then minus 2 amps and then 2 amps and then minus 2 amps and then 2 amps and minus 2 amps. And it's doing that at a period, at a rate specified. So for instance, 1 time a second would be half a second on and half a second off, or half a second, say 2 amps, and then half a second at minus 2 amps. And we'll be going over frequency and period later in the class, so you don't need to worry about what that means. So now let's talk about voltage. Voltage is also associated with circuit elements. So we looked at current a moment ago, which is the time rate of charge, right? And the amount of charge per second. How many coulombs per second are we sending through a circuit element, whether that circuit element be a wire, that circuit element be a resistor, that circuit element be, as we'll discover later in the class, an inductor or a capacitor or an operational amplifier or a diode, so on and so forth. Every circuit element we're going to send charge through, and also measure the voltage across the circuit element. And you measure that in units of volts, and those are joules per coulomb. So just the actual definition is the electrical voltage associated with a circuit element is the energy transferred per unit charge that flows through that element. So joules per. So for here we have circuit elements 1, 2, 3, 4, and 5. And correspondingly, we have voltage 1, voltage 2, voltage 3, voltage 4, and voltage 5. It is important to pay attention to the direction of the positive and negative sign. So for instance, for voltage 2, we would measure it from the positive to the negative terminal. For voltage 3, positive to the negative terminal, so on and so forth. Always, again, pay attention to what you assign as the person doing the circuit analysis is the voltage polarity, so that when you apply Kirchhoff's voltage law, you apply it correctly in your equations. So here, for instance, we have a circuit element. This is a resistor. We have a voltage VAB that we'll go ahead and point out here. And that is the voltage from terminal A to terminal B, where positive is A and negative is B. So let's say that the voltage across this resistor was 5 volts. So VAB was equal to 5 volts. So it means there is a positive 5 volts from here to here. If we were measuring it with a multimeter, for instance, we would measure 5 volts from terminal A to terminal B. The red wire would be on A and the black wire would be on B. Now, if I asked you what is VBA, which means the voltage from B to A, you would flip your multimeter around and you would put the red wire on B, put the black wire on A, and it's going to be exactly the opposite value. So if 5 volts was equal to VAB, VBA would be equal to minus 5 volts. So pay attention to, if you see this kind of nomenclature where you have an explicitly labeled terminal name, like VAB or VBA, that means the voltage from A to B or B to A, and it's referring to the leading letter of the terminal is the positive terminal in this case. So in this case, it's referencing B is positive. However, if we had 5 volts across it from here to here, then correspondingly it would be negative in this case. So now let's talk about electrical power. So the definition of electrical power is associated with a circuit element and it's measured in joules per second, and its unit is in watts. So the simple formula is, and it's true for everything we're going to learn in this class, is voltage times current. And remember, voltage is joules per coulomb and current is coulombs per second. So what we end up with is just simply P is equal to V times I. And of course, this could have a time component. So voltage is going to vary with time. Current could vary with time. So this could be V of t times I of t, who gives us power of t at a specific time. And of course, the formula is just joules per coulomb, coulomb times coulombs per second. The coulombs cancel out, and you end up with joules per second, which give us the unit watts. Energy in the end is the integration of power over the specified time. And this is just simply going to be in joules. So you're getting rid of the seconds component effectively. So you're just going to integrate P of t over dt from time 1 to time 2, whatever it is, or you can just simply do the Vt it dt. So in summary, we have today talked about electrical voltage, electrical current, power, and energy. So an electrical current is just simply coulombs per second, so the time rate of change of charge over time. Electrical voltage is the amount of energy for the specified amount of charge, so joules per coulomb. Power is in the end in the units of watts, and that is current times voltage, so P is equal to V times I, and it is joules per second, and energy is just the integration of power over time, giving you a total amount of joules that was done, basically the work, the energy that was expelled or absorbed in a circuit. So either supplying energy or absorbing energy. So, and we're going to be talking about this more in detail as we go along, but this again is just a general introduction to the concepts of this class, because this class is going to focus on transformation of power through the use of current and voltage. And we're going to have all of these different analysis methods and ways of determining the voltage and current going through different circuit elements. So again, this was a review of what you would have already had in your physics lectures.